Hello everyone, I welcome you all. This is Lata, working as an assistant professor in the Department of Chemistry at KVN Arts, Commerce and Science College, Nasik. In today's lecture, we are going to discuss about the biogenesis of manure, sclereol, quarine, steviol, abietic acid, taxadiene, and Forskolin from geranyl pyrophosphate, that is GGPP. In today's lecture, we are going to discuss about the diterpenoid. The diterpenoid consists of C20 units. The diterpenoids arises from GGPP. GGPP, that is geranyl pyrophosphate or diphosphate, which is formed by the addition of IPP molecule to the FPP, where FPP is farnesyl pyrophosphate or diphosphate and IPP means isopentenyl pyrophosphate. Now the first structure of FPP, here double bond, here CH2, here CH3, here double bond, CH2, here methyl group, here is double bond, and here OPP. So this is FPP. So in first step, loss of pyrophosphate from this FPP, and we get, here is double bond, CH3, here CH2, here methyl group, here double bond, and here positive charge, that is allylic cation. In next step, addition of IPP. This is IPP to this allylic cation, and we get, here is double bond, CH2, here CH3, here double bond, here CH2, here CH, here is methyl, here double bond, here become CH2, here methyl group, here CH2, and here OPP, and here tertiary carbocation. So in next step, here hydrogen. In next step, stereospecific loss of this proton, and we get GGPP. This is called as GGPP, that is geranyl pyrophosphate or diphosphate. This structure you can also write in this way. Or also written like that. All these structures are equivalent. Now we will see the biogenesis of manure from GGPP. So first, write down the structure of GGPP. Here OPP, CH3. So in first step, protonation of this double bond gives tertiary cation. This allows the series of concentrate cyclization. These double bond attack on this double bond, and these bond attack on this bond, and here H plus, that is protonation, take place with the cyclization, and we get tertiary here CH3 and here positive charge. In next step, here minus H plus from this methyl group, and we get and this is known as copalyl pyrophosphate. There are two isomers of copalyl pyrophosphate. First one is this one. Then this methyl group is above one side and this hydrogen below the side. This hydrogen below. This is called as plus copalyl pyrophosphate, and another isomer is this methyl group is below the side and this hydrogen is above. This hydrogen is above. That this is called as minus copalyl pyrophosphate. So in the biogenesis of manure, we use plus copalyl pyrophosphate. So here this is plus copalyl pyrophosphate. From this copalyl pyrophosphate, in first step, loss of this pyrophosphate take place and we get only cation. Here positive charge. In next step, rearrangement of this positive charge and we get here tertiary cation. So in next step, on addition of water molecule, we get here is double bond, here CH3 and here OH, here Me above the plane, here hydrogen below the plane, here hydrogen below the plane, and this carbon is above the plane. So this is biogenesis of manure from GGPP. Now we will see biogenesis of sclereol from GGPP. So the first structure of GGPP. So in first step, protonation take place of this double bond and with cyclization. So these bond attack on this carbon, these bond attack on this double bond, and here protonation take place with formation of carbocation. So the next step, on addition of H2O, we get here OH. So in next step, loss of pyrophosphate take place, that is minus OPP, and we get allylic cation. Here CH3, here OH. In the next step, rearrangement of this carbocation, and we get and here positive charge. In next step, on addition of water molecule, we get hydroxy functionality, and here OH. Here this methyl group above the plane, and this is known as sclereol. This is all about the biogenesis of sclereol. Now we will see the biogenesis of quarine from GGPP and biogenesis of stavol from quarine or GGPP. So the first structure of GGPP. So then first step, protonation take place with the cyclization. These double bond attack on this double bond and these double bond attack on this double bond, and here protonation of this double bond take place with cyclization, and we get here positive charge. So in the next step, minus H plus take place. That is loss of this proton, and we get here is double bond, and this is known as covalent pyrophosphate. In next step, loss of pyrophosphate, and we get generation of cation. In next step, cyclization of alkene onto this cation, and we get here positive charge, here methyl, here double bond. In next step, cyclization of this alkyl onto this carbocation and produces secondary carbocation. So we get here and get here new secondary cation. In next step, Wagner-Merwin 1,2 alkyl shift take place on this electron deficient carbon atom, and new formation of cation take place. Here positive charge and here methyl group. So the next step is 1,2 hydride shift of this hydrogen on this carbon atom and get new carbocation, and we get here a positive charge. In next step, minus H plus take place from this methyl group, and we get here double bond, and this is known as quarry. So the next step, sequential oxidation of this methyl group to the carboxylic acid via alcohol and aldehyde. So we get here CO2H, that is carboxylic acid, and this moiety of this compound is called as Terpenoid acid. In next step, on addition of NADPH, we get successive oxidation of this carbon, and we get this is known as stevie. Write down the structure in this form. Here methyl, here CO2H. Here OH, and here double bond stevia. Now we will see the biogenesis of acetic acid from GPP. So the first structure of GGPP. So in the first step, protonation take place with the cyclization, and we get carbocation here. And in next step, the loss of minus H plus, and we get covalent pyrophosphate. So all these two steps are showing last genesis. So I cannot repeat this and directly write down here the structure of copal pyrophosphate. Abatic acid is synthesized from the plus copal pyrophosphate. So the next step, loss of pyrophosphate, that is here minus OPP take place and we get allylic carbocation. So the next step, cyclization take place with formation of new double bond and we get here new carbocation. Here positive charge, clearly double bond, and this cation is called as Sandara Kopi Marinil cation. In next step, intramolecular transfer of this proton, formation of secondary cation. Here methyl and here secondary cation. In next step, Ullmann 1,2 methyl shift take place on this carbocation and we get new here is methyl and here positive charge, and this cation is called as abatinil cation. So in next step, loss of these proton take place and generation of dye and we get and here two methyl groups, here CH3, here hydrogen below the plane, here hydrogen below the plane. This methyl is above the plane and this methyl is below the plane, and this is known as minus Avhad dye. So in the next step, with the help of O2 and NADPH, sequential oxidation of this methyl group to the carboxylic acid via alcohol and aldehyde, and we get abatic acid CO2H. And this is minus abatic acid. And this is the biogenesis of abiotic abatic acid from GGPP. Now we will see the biogenesis of Taxadiene from GGPP. So the first structure of GGPP. So in the first step, loss of pyrophosphate take place, formation of cation. So we get the next step, electrophilic addition to this carbocation and formation of new tertiary cation take place. Here is positive charge, here CH2. In next step, this double bond attack on this carbocation and we get new tertiary cation. Here is positive charge. Here is methyl groups. Here is double bond, here CH2. And this cation is known as verticinil cation. In next step, intramolecular transfer of this proton and we get new tertiary carbocation. In next step, electrophilic addition to this carbocation and we get new carbocation. This cation is called as Taxadiene cation. So the next step, loss of this proton take place and we get Taxadiene. Here is double bond. This is all about the biogenesis of Taxadiene. Now we will see the biogenesis of Forskolin from GGPP. Structure of GGPP. Here OPP. So the first step, quenching of intermediate by water molecule. So here lone pair of oxygen is attack on this carbon atom. This carbon attack on this carbon. This double bond attack and here H plus take place and we get here methyl, here OPP, here CH3 and here OH. In next step, loss of OPP and we get formation of cation. In next step, quenching by attack of this hydroxy gives heterocyclic ring. Lone pair of oxygen attack on this carbon. This double bond shifted Fourier and we get here oxygen, here methyl, here methyl hydrogen below the plane, here hydrogen below the plane, here methyl above the plane and this double bond below the plane. In next step, selective oxidation reaction take place. This and this carbon atom and we get here OH, here methyl, here oxygen, here OH, here OH, here OH, here methyl. This double bond. In next step, selective oxidation of this hydroxy molecule and esterification of this hydroxy and we get here OAC, here OH below the plane, here methyl above the plane. Oxidation takes place here in this carbon double bond oxygen, here methyl group above the plane and this methyl group below the plane and here OH. So this molecule is called as Forskolin. So this is all about the biogenesis of Forskolin from GGPP.